something called nystagmus, or a complete field of vision. Far from the exemplar of the body's perfection, the eyeball is a device which, if it were designed by a camera engineer, would result in mass firings immediately. It doesn't have to be that way. The eye of the octopus is designed properly, with the nerves and vessels penetrating the eyeball from behind, wherever they're needed, no blind spot, no need for nystagmus, no retinal detachment, a better design altogether. So the question is, why is the human eye so vulnerable while the octopus eye isn't? Well, it's just bad luck, just simply bad luck. The layer of cells that initially became light sensitive in our ancestors was in a superficial cup, and gradually tissues unfolded around them, leaving the vessels between the light and the receptors. In the octopus, it happened in a slightly different way, leading to an eyeball that is right side out. This seems surprising. Health is not, in fact, selection's goal. Selection is shaping whatever benefits reproductive success, and usually staying alive a long time and healthy benefits your reproductive success. However, what if there's a gene that increases reproduction at the expense of health? Are there any examples? Well, there are two. One is senescence, that is aging, and the other is the feeble sex. I first got interested in evolutionary approaches to medicine by trying to understand, as an undergraduate, the origins of aging. Aging is strongly heritable, so why does natural selection just make individuals live longer and longer? One explanation, proposed by George Williams in 1957, is pleiotropic genes. Some genes offer advantages early in life when selection is stronger. George offered the example of a gene that made bones heal faster, but that also simultaneously, very gradually deposited calcium in the coronary arteries, eventually by some age of 120 or something, killing everyone. Not all genes causing aging are such pleiotropic genes. Others have simply never been selected for because they have little cost in the wild, because everyone is dead by that age. Implication: aging isn't useful, but it is shaped by selection. Here is a graph that makes the point. I, or Y, stands for individual reproductive years. Notice for this species, the number of individuals starts at 1,000 and most of them die before the age of 2. Reproduction begins at about the age of 4, that's the vertical dashed line. And then the rate of death goes down fairly steadily until about age 8, and then much more suddenly until almost all individuals are dead by the age of 11. The dotted line is an imaginary group that has no senescence. That is, the mortality rate, instead of increasing, stays exactly the same as it was at the age of first reproduction. By comparing the areas under the curve, I or YA, which is actual, versus I or YH for hypothetical, one can get some very rough estimate of the strength of selection acting on a particular species. Of course, to do this, you have to find data from the wild about populations of species. Here are data I was able to extract from published literature in the mid-80s. Now this has been done quite a lot better, but it makes the point that with simple calculations you can make estimates that help to differentiate species where senescence is actually quite a strong force of selection, and those where it really doesn't influence fitness much at all. Here's another fantasy in the form of a graph. What if, just say for instance, the mortality rate stayed the same throughout life as it is at age 20 in the United States in 1988? Well, instead of the population declining very suddenly and everyone being dead by age 100, almost 40% of individuals would still be alive at age 1,000. The purpose of this is just to dramatically show the extraordinary force of selection on senescence. Just as an evolutionary perspective suggests different questions to ask about mortality rates, it also suggests new places to look for the origins of disease. Developmental pleiotropic is one. Only a tiny, tiny fraction of sperm ever fertilize an egg, and only about 20% of all fertilized eggs ever go to term. Here, this is very powerful selection acting just in the first few days after conception. A mutation that gave a tiny incremental advantage at these stages would spread, even if it caused disease later. Several such genes have been proposed, but none have been confirmed as of yet. There's much to be done in this area. defenses and suffering. Why on earth is life so full of pain and anxiety, to say nothing of headaches and nausea and vomiting? Well, it's because these painful responses are in fact useful in certain circumstances. In fact, the very fact that they're painful is part of their utility. Pain and suffering indicate problems, but they are themselves solutions. As with so many other topics, Darwin said first, mere suffering of any kind, if long continued, causes depression and lessens our action. It is well adapted to make a creature guard itself against any great or sudden evil. There are two quite distinctly different kinds of problems that bring people to the doctor. The first are defects, things that just aren't working right in the body. Seizures, cancer, paralysis, jaundice, injury. These are things where the machine is simply broken. Most of the reasons people come to the doctors are not direct manifestations of disease, however. They're defenses, that is, the body's responses that are protective responses to disease. Fever, cough, pain, fatigue, and anxiety are all useful responses that are kept in reserve until the situations that arouse these situations in which they're useful. Of course, defenses need to be expressed only in those certain situations where they're useful. And boy, oh boy, does it seem as if they're expressed too often, too much, too long. How come? We can block them safely too, using drugs like codeine to stop cough or aspirin to stop pain. Did some mistake get made in design of the organism? George Williams and I have called the relevant principle the smoke detector principle, because just for the same reason that we put up the smoke detectors that go off when we make toast, our bodies express defenses quite often when there's no major danger actually present. Here's how it works. The body has to monitor some cues associated with danger, the number of bacteria in the stomach or the temperature of the body or something. If the cost of the defense, say vomiting for instance, is less than the expected reduction in harm from the danger, then it's worth expressing the defense. That is, when the cost of the defense is less than the cost of the harm without the defense minus the cost of the harm with the defense. But what if it's not perfectly clear whether the danger is present? Say you're in Africa and you hear a sound behind a large rock. It could be a lion or it could be a monkey. Should you run? Well, it all depends. It depends on the cost of the defense, that is, the cost of running, even if there's no lion there. It depends on the cost of harm. If you don't express the defense, that is, if there is a lion there and you don't run. The cost of the harm, if the defense is present, that is, how likely a bad thing is to happen if you do run, and the probability that the harm is present, that is, the signal-to-noise ratio, the overall baseline likelihood that it's a lion versus the probability that it's a monkey. The optimal system will express the defense whenever the cost of the defense is less than the probability of the harm times the cost with no defense minus the cost with the defense. The optimal response threshold can in fact be calculated. We won't go through the math here, but it depends on the probability of noise versus probability of the signal and the values of rejection, false alarms, hits, and misses. A specific illustration will make this more clear. Say you hear a noise behind a rock. Should you flee? Well, if the cost of fleeing is 200 calories, and the cost of not fleeing, if there's a tiger there, is 200,000 calories, the optimal response is to flee whenever the probability of a tiger is greater than 1 in 1,000. This leads to a quite profound conclusion that panic, that is running away as fast as you can, is perfectly normal if the noise means that there's a 1 in 1,000 chance. This also means that 999 times out of 1,000, there will be no real reason to flee, but it's still perfectly normal. Many instances of aversive emotions are useless, but perfectly normal. If this fellow is coming towards you, you need to decide what to do. And in one of my favorite quotes from behavioral ecologist Lima and Dill, they say, few failures are as unforgiving as failure to avoid a predator. Being killed greatly decreases future fitness. This is almost relevant in the clinic, where we see plenty of patients with panic disorder. Panic disorder is nothing more or less than an emergency reaction going off at times when it's a false alarm. This is illuminated by the smoke detector principle, and for a certain portion of patients, just explaining that this is a false alarm and a useful system is all they need to know. This principle also has the perhaps profound implication that this is why the general practice of medicine is possible in some